So after a long video giving you the intuitive explanation for Flux, you started with the very simple case of constant flow on an area that is perpendicular to the flow. Then we added areas that are not perpendicular to the flow, so then you had this cosine, which could be written as a dot product. So then you knew that the flux for a constant flux density and a vector area vector A is given by this dot product. And then I asked, what if the current density and the surface are not constant and the surface is not flat? So how do you calculate the flux? You have to do an integral of differential flux. And the differential flux is just the flux through a tiny amount differential of surface ds. So on this differential of surface, we can assume that the flux density is constant. So the dot product of j dot ds gives you the differential of flux, which we just add up throughout the surface. So that makes us arrive at the integral definition of a flux. So the flux of a vector field f over a surface S is defined as the surface integral over the surface S of f dot ds. Okay? Now notice that now I switched to using f instead of j, okay? Because I want to be more general. So f looks like a more general, any vector field f, we can calculate the flux of this field through a surface S. Please, I highlight this. I drew the dot very big on purpose. This is a dot product, and you must never forget. Okay? You must never forget. Now, this ds is a differential of surface. So what does this ds mean? So ds is a vector differential of surface whose length is equal to the differential of surface that you studied in the previous sections, and whose direction is n hat, the direction normal to the surface. Okay? So we could say that this is the definition of this ds vector. So now I guess my question to you is, how can we get ds vector? So let me refresh you how we calculated ds as a scalar, because they will have the same length. Okay? So ds as a scalar was calculated by calculating this here, which was the length of the normal vector n, which is calculated as the cross product of the two tangent vectors, which are partial derivatives, times du times dv. Okay? So now if we want to obtain ds vector equal to ds, but in the direction of n hat, well, actually, we are very lucky, right? Because this term here, without taking the length, so if we removed this calculation of the norm, this term here would be the normal vector. And the normal vector is already, by construction, it's already pointing normal to the surface. So this normal vector is already pointing in the direction of n hat. Okay, so this is great news, because it means that to calculate ds as a vector, we just have to remove the calculation of the norm, so that we leave the direction of n. Okay, let me justify that mathematically instead of doing an argument. So if we say that ds was equal to the norm of the normal vector times du times dv, that was the definition of ds. But we will also say that n hat, which is a unit vector perpendicular to the surface, we could very easily define it by saying that this is the normal vector n, but divided by the length of the normal vector n, so that it is a unit vector, right? And therefore, if you want to find ds vector as the product of ds times n, then you are getting the norm of n times du times dv times n vector divided by the norm of n, which means that the norms of n cancel out, and you end up with n times du times dv. Okay? So I hope this mathematical argument convinces you of the way to calculate this ds vector. And therefore I can write it down here. Ds vector is calculated as the partial derivative of r with respect to u cross the partial derivative of r with respect to v And this is a vector, which we have called the vector n, times du times dv. And this I wrote in a golden box to indicate that it is a very important equation. Okay? So that is how we calculate ds. So in order to do this flux integral, we have to parameterize the surface, then we have to calculate ds using this formula, and then, very important, we have to do the dot product between the function that we are integrating and ds. They are both vectors, and we need to do the dot product because the flux has to be a scalar. So whatever is inside of the integral must be a scalar. That's why it's important to remember the dot product. Okay? So thank you very much, and see you in the next video. In the next video, I'm going to do a step-by-step recipe for calculating flux integrals, okay? And in particular, I will show that there are other ways of finding ds. So you don't necessarily have to do this equation. You can also do it by geometrical intuition or by looking it up on a table, okay? So see you in the next video.